as the outline says, this is a short note on multi-level multi-integration and its application to evaluate integral equations such as the elastic deflection type. And it starts from the SAINT-VENANTS principles, and then guide you through some important aspects in the existing literature on MLMI. And the lecture ends with a comparison between the DC-FFT, direct convolution, fast Fourier transform based technique, and the multi-level multi-integration based technique in terms of both accuracy and efficiency. So for the reason of completeness, here follows a short note on multi-level multi-integration. And this is actually built upon the SAINT-VENANTS principle, which tells us that if we alter the pressure distribution without affecting the resultant force, so if the load balance is still the same but we have a slightly different pressure distribution, could be for example due to different surface roughness, then we can exemplify this in our half space situation like this. So we have a pressure distribution localized at some place, and we can see we have some very specific characteristics of it relating to roughness or whatever it can be, and we see the deformation in the half space, okay, schematically, but still it comes from a numerical computation of the deformation as we have learned how to do before. And if we just change this pressure distribution a little bit, as you can see now, still maintaining the load balance, we have a slightly different deformation field, but if we measure it at that point, the very same place, it will be more or less the same, regardless of the little changes, the local changes in the pressure distributions that we imposed here. So, in other words, to calculate the deformation at a distant point, as we saw, we can lump this pressure distribution together. We don't have to resolve it so much, and we can get a very good approximation of the deformation at a relatively coarse mesh. So, and here is a very coarse mesh if it only has 3 nodes, but we can think of its 3 nodes somewhere in the grid or mesh of much bigger size. Anyway, if we correct now, we have the results here. We know it's not perfectly correct, but the multi-level multi-integration routine builds on now performing a fewer amount of operations than for the whole summation required to compute the deformation at a certain grid. We compute a fewer numbers of those at a finer grid, correct the results, we carry on, we have an even finer grid, correct the results, we have an even finer grid, correct the results, and by doing this we end up with a result which is very close to the numerically exact deformation, but we have not carried out as many calculations as we would have if we carried out the matrix vector multiplication in full. Okay, there is something that you should be aware of when you dig into literature publications on this subject, and that's this mesh size which is denoted by H. And here we see we have the multi-summation, or the summation, which we've already been familiarized to before here, but now we have added this H to tell that okay, it's discretized with a certain mesh size H. Okay, and we find this H outside this integral a little bit mysteriously, but let's keep it like this and see what it looks like in the literature. And then if you want to really find out where this H comes from, you have to read in the paper by Brandt and Venner from 1998, and here you really have the full representation of the summation that you should carry out on a grid with mesh size H to get the deformation. But let us now compare this. Here is another way of formulating it, and that would be add this H to the power D in front of that integral, and you should compare this now with what you saw before, and what you saw before is actually the correct the correct way of expressing it. But now we have instead pull this H to the power D, the mesh size to the power D, outside the summation. And this is not only found in one publication, it's in many publications, and here you have one by Wang et al. From 2003, which we will look into a little bit more when we compare the efficiency and the accuracy of the DC-FFT method and the multi-level multi-summation methods. And here you see that they have represented the deformation at one grid with the lower letter H as step size, meaning that's a finer grid than the capital letter H step size. And they also defined in equation 15 down here the deformation at that grid level. But you can clearly see now that they scale. It looks like the summation is scaled with H, but you know already that the step size is not outside that kernel. It's actually inside the kernel. It's inside the logarithmic expression for the discretized kernel. So this is more or less just a schematic view of it, I would say. So be a little bit careful. You check out the paper by Brandt and Venner for the very details, and please have a look in the book by Venner and LUBRICATION, which is really nice work on multi-level methods in lubrication. And you have not only the multi-level multi-integration, you do also multi-level techniques to solve the Reynolds equation, including elastic deflection as a total. And that's this book is sort of a Bible in this sense. You should have a look. There's lots of important aspects dealt with in it. Okay, so just to sum up, we compare now the MLMI, multi-level multi-integration, with the DC-FFT method, and we already know, and this image also depicts, that we have numerically exact solutions in the DC-FFT case for a Hertzian pressure, for example, but for any example that we can compute in the standard way, matrix vector multiplication, we will get an identical result numerically by means of the DC-FFT method. And back in 2003, when this was published, they had a Pentium 4 1.5 gigahertz CPU, and I mean the architecture is very different, so even though the numbers, the frequency is not so much greater today, the architecture is much more sophisticated, and therefore we compute things lots faster today. This machine appeared to have 256 megabytes of memory, and they had implemented these routines in Fortran code, which is compiled code, and it's very fast. And you can see the times here. And if we look at the little bit larger meshes where they were able to compute things for or on, the 2 to the power 8 squared and 2 to the power 9 squared meshes, we can see that the direct summation took them 2 minutes in the 2 to the power 16 number of degrees of freedom case. But if they apply the multi-level multi-integration, they were down at 2 seconds, so from minutes to seconds, and then even little bit shorter time with the DC-FFT, and this is due to the overhead cost. Setting up the multi-grid routine is a little bit bigger than doing the FFT. Then you increase to 2 to the power 18, and you see now we're 2/3 of an hour now, 2,600 seconds to compute the direct summation, and then probably you have leveled out what you can manage to do with the memory wise with 256 megabyte memory. And then the multi-level multi-integration, it scales up to 6.5 seconds, and the DC-FFT to 2 seconds. Still a factor of 3 between them, but they could be closing in later on. It's not a big difference. I mean, the huge difference is between the direct summation and these two very efficient routines to compute the elastic deflection. Now, just for fun, I made actually a similar comparison myself on my MacBook in 2015. I bought it new then. It was actually running this Mac OS Mojave, and it's a pretty nice spec on that machine. It was 2.8 gigahertz Intel processor, Intel Core i7 processor, and I 16 gigabytes of RAM, and I ran MATLAB 2015B on it and obtained these times. So for 2 to the power of 15 nodes, I was at the multi-level. I was at the direct summation at nearly 2 minutes time, which they were actually with Fortran in 2003 at 2 to the power 16 nodes. So 2003 they definitely beat me on the direct summation with Fortran. And looking at the timing for the DC-FFT, it was 0.12 seconds. Compare this with the 2 to the power 16 nodes 2003, they were down at 0.44 seconds. So actually performing the DFT was a little bit the DC FFT was a little bit faster for me with 2 to the power 15 in comparison to the direct summation was, but still not as good, I would say, as they had in 2003 with Fortran, but close. Now to 2020, I have this iMac on my desktop, and it's a little bit faster, and another architecture is an 8-core apparently i9 Intel processor, and I have 32 gigabytes of RAM, and I continued the process. You can see it really increased the speed on 214 and 215 number of degrees of freedoms, and I continued that to 216 and then 218, and you can still see if you have 2 to the power 18 nodes, and it's only 0.013 second computation time to do the DC-FFT, and here we actually beat now Fortran in 2003 because they had 2 seconds to do that computation. So we're clearly beating them here. And I also took some time and checked the Moore's law, stating that there is a doubling of the efficiency of the computational power, or the power of the PC every 18 months. And actually it was more or less exactly this ratio if you look at numbers from 2015 and 2020 that I have produced here. It's actually it becomes more than 8 times faster in less than 5 years. So it's true, Moore's law is true, but perhaps it's more to it than just these numbers. But they align to it nicely, and I thought it was interesting aspect to tell you about. Now the accuracy. So here we have in red, we have the direct summation. So that's what we compare against, I would say. So we have, I mean, the relative error there is just the numerical discretization error from the continuous result, and then we have the FFT result in white, and then we have the MLMI in blue, and we can see that the white, the FFT, is identical to the direct summation because it's numerically exact. And we can also see that the multi-level multi-integration is more or less identical. There's a little bit of a difference there, but nothing to be bothered about. Some concluding remarks on this. So the DC-FFT method, as you have seen, and I hope I have been able to show to you, it implements easily. It has a numerical exact elastic deflection computation, but also any type of convolution of this kind can be computed numerically exactly. And it has a very fast evaluation, n log n correspondence to computation time. And we've also seen the MLMI, multi-level multi-integration, perhaps not as easy to implement. It's still an interesting methodology, and it is excellent accuracy of the approximation. Okay, not perfectly numerically exact, but all or nearly numerically exact, and it evaluates nearly as rapidly as the DC-FFT. Then here in brackets I have added the CC-FFT method, so the way of first finding the continuous transfer function for the integral equation at hand, then discretizing that continuous transfer function, and then multiplying that in Fourier space with the Fourier transformation of your pressure, if it's an elastic deflection, or of the other function in the convolution, and then you can invert this result to obtain the value of the integral equation. It is very good for understanding the behavior of your integral equation, but it is not so nice when it comes to numerical accuracies, especially if you have rough surfaces involved when you're trying to compute an elastic deflection, or even if you have Hertzian pressure, this is the Hertzian contact, which produces a Hertzian pressure distribution, and the Hertzian pressure distribution has very sharp gradients where it becomes greater than 0 at plus minus 1. So even at that case, you have to be a little bit careful when you apply the CC-FFT method. Still you can get a very accurate result, and it's a method worth knowing about, I'd say, because it may be provided a continuous transfer function, and by means of this you can analyze the behavior of your integral equation at least.